Okay, is this it? Where is everybody else? Is this all of you? Weird seating arrangements. So, 23 days to go, 23 wake-ups to go.
Differenti cursos su fare.
Alex. Thank you for telling me. William. Right, so DC, AC, generating electricity, electromagnetism, yeah? Woohoo! Ready for some physics? Everybody look happy, not. Are all your national tests over?
No.
Yes. Well, this is the end of term. You can hopefully start to unwind and de-stress now. Hopefully. And I can probably start taking back your ILMIA books. Start nagging you on that.
I'm collecting them in my library.
Excellent. Okay, and you've got your names written on there. Okay, so Anna said that you talked about AC and DC, and now hopefully I'm back, if I'm well enough. So sorry, we're about to get all sorts of distractions in the way we talk. We've got quite a lot to do still, depending on how far or how many lessons we've got after your trip and stuff like that. My idea is to talk about how electricity is generated on in a power station, and then nuclear power, and then if we get a chance, astronomy and cosmology, but I'm not sure. But we'll try.
Are you teaching us now?
Yeah. Hopefully now, I'm back full time, hopefully, provided I don't start getting sick and dizzy. Okay. So, this lesson, I am recording it, but hopefully there won't be any need to take notes, unless you're doing wonderful doodles, as you do. Round the front, I want to explain how shoey helmet is that? How shoey helmet is that? Are you allowed to have a dark visor?
Yeah.
What about at night? Do the police should the police, if they catch you, make you take the visor off at night? No, you're allowed. Okay, right, so we have two main types of electricity. We have the AC, which comes out of the wall, which is what we use every time we plug something into the wall. And we have batteries, which is what our phones run on. However, we have to plug our phones into the wall, our phone chargers into the wall, so we need to change that electricity, AC, into DC. This is one device that allegedly does it, a power supply. Okay, so this is our expensive battery. This is, I don't know, 10 years old or so, and it's about €200 worth. They are a huge investment of money, these power supplies. And we put in 230 volts here, or 220, and then we get out a smaller amount, up to 12 volts, we get DC and we get AC. Please do ask questions as we're going along. So, red and the black, traditionally red is the positive, and black is the negative, so that's better. It works if you plug it in. Okay, so there I have 3 volts DC. Let's have a look at what 3 volts AC looks like. Brighter or dimmer?
Same.
Okay, 2 volts.
This is great.
This is brighter. Yeah?
Yeah.
Or hardly noticeable. Okay, actually the DC is going to be a little amount brighter because with the DC you've got the value always being, that's time, that's voltage, you've got it always being at 2 volts, whereas here you've actually got with the AC sometimes where it's dropping to 0 and you're getting an average current. I know you're cleverly looking at that and saying, if that's 2 and that's -2, isn't the average actually 0? Why do we get, well, no, because it's to do with energy and that's to do with squaring the signal, etc., etc. So they are actually slightly different. DC is always at that value. So if you grab hold of a electric fence, electric fences, the countryside, keeping the horses in, people out. If you grab hold of it like this, it's probably going to be at about 24 volts. It's always going to be at 24 volts, and it's always going to hurt.
Why is it just 24?
Because usually they run off car batteries, which are 24 volts DC, I believe.
They're DC.
They're DC. Car batteries are DC. Chemical batteries are DC. So the liquid lead plate, the acid and lead plates are DC. If it was, however, AC, like you get an electric shock from this, when you grab it, sometimes it's at its highest value, and here as well it's at its highest value, it's just going the other way, but other times it's actually at 0, and it gives you a shock like that, only that is 50 times a second. That's good though, because it does give you a chance, hopefully, to pull away from it, because it's not always at that highest value. So DC shocks tend to be worse for you. This device changes our electricity to the value that we want, because if I plug that poor little bulb into the wall, it would blow up. That bulb only wants to be working at 5 volts. Your mobile phone battery wants to be working at about 6 or 7 volts, something like that. And yet you plug it into the wall and it comes out at 220. So you cannot plug your phone directly into the wall. And now we have the almost universally used devices. Though apparently Apple don't like to use them, the micro USB. Yeah. So instead of having a plug like this, where you simply have got wires going in, connect them up with a single joint wires going out, you have the wires going in, and then you have a bunch of circuitry inside this to change it to 5 volts coming out. Yeah, and you could have a little USB adapter in there. So inside this device is a transformer of electrical voltages and electrical currents. And it's tiny, and it probably is 99.9% efficient. When you touch it, when it's plugged in, it will feel warm. Yeah, the warmer it is, the less efficient it is. If you feel it's getting too hot to touch, you need to unplug it and throw it away. No, take it to also go for recycling, okay, because it's dangerous. Okay, I'm going to show you what is inside this and how some of those inefficiencies can be improved. For that, I need to have some AC and I need to make a magnet. For the electromagnet, I'm going to need to have a coil. So I've got some coils of wire here, 600, 200, 400, let's have a 600, that's the biggest one. And I now have electricity going through the coil, and hopefully you realise that when electricity goes through a coil, it makes a electromagnet. Yeah? Yeah, so that's the motor effect. There we go. Okay, if I put the coil over something that can be magnetised, do I get more or less magnetism? More. Okay, it's quite dramatically more compared to no magnet. Okay, it was a little bit further away. Okay, so I now have made this into a magnet. Made it into quite a strong magnet. Okay, that's with DC. What happens if I do it with AC, which remember has got this changing pattern? Well, the current isn't the same all the time. And in fact, the magnetism is changing direction. It is magnetic.
Not very strong.
Not very strong, no, because our poor little compass is totally confused. This is flipping, when it's switched on, this is flipping from north to south to north to south, 50 times a second. It's got an alternating magnetic field, okay? And it's not very strong, but there you can hear it.
It's changing.
It's changing. That buzzing, if it was 100% efficient, we wouldn't have the buzzing, okay? What's happening is 50 times a second, this bottom part here, let's say it's north at the top, and it's pulling this down, making that part into a south. Then it's flipping, and that's a sort of south and the north. But as it's flipping, some energy is wasted, and it's actually making this top part vibrate. I can set it up so that the vibration is really, really inefficient, and you can hear it quite loudly. If you ever hear your phone charger start buzzing, please unplug it, okay? Because this is losing a huge amount of energy, and if there is a huge amount of energy being lost, then it's at risk of creating a fire, because the energy normally ends up as heat. Okay, there I've got it connected up a little bit, noise or anything, so it wasn't so much. Okay, so this is the start of a transformer, and a transformer, sorry, it's sadly not robots in disguise, but a transformer is something, an electrical device that is going to change the voltage that goes in and the current that accompanies it into something useful that we can put out. Okay, any questions so far? Right. There's one of these in here. There are loads of these at Twitter. Wherever you see a little hut or cab or box or something by the cycle path where it says danger of death on it with the spark, there are loads of these in there as well. And sometimes they are making the electricity come out higher, sometimes they are making it come out lower. Through an amazing process involved.
Higher.
Sorry?
How can you make it higher?
The energy that you're putting in is a combination of current times voltage times time. Okay, the energy that you put in hopefully is going to be the same as the energy you put out, you take out, maybe a little bit lost as heat. If you mess around with the two things that you can play with, current and voltage, you can put in a high current and a low voltage, and you can get out a low current and a high voltage. So it's an interplay between the two. Very, very, very useful. Okay, so I've got 600 turns on this. I am going to change it to a slightly lower version, 400. And I'm going to put that in there, doesn't matter which one I put it on. And then I'm going to have 600 turns on the output. Okay, the output's going to be here, like that. And I'm going to connect this to a bulb here.
So is this now kind of the same as that current?
Yes, on a very, very low scale. Now, why is this not working? Oh, who have I got there? That's better. Okay. So I've got a little bulb there. So yeah, okay, that's fine. There's a load of wires connecting it. Well, no, there's not. This is not connected to the power supply in any way, except magnetically. Magic. Wireless transmission of electricity. Bizarre. Okay.
Does wireless chargers have the same thing?
Yes. But the technology has been very, very slow for all sorts of different reasons as to how it's been developed. The simplest example of where you have got a non-electrical transmission, where it might be quite hard for you to realise how does this actually work when you're charging something up, is an electric toothbrush, one that you plug into the wall, and then you've got the plastic toothbrush and you put it on the charger. The charger is covered with plastic and the toothbrush is covered with plastic. There's no electrical contact there, it's all plastic. And the electricity can't flow through the plastic. Does that make sense? Yes.
So how do you control it?
How do you control it? Okay. Right, if we say that that is the toothbrush and that is the charger, and this on the outside is all plastic, what you've got is an electromagnet down here. Yeah, and you've got the electromagnet here. So the input makes the magnetic field. That creates a magnetic field up here, and there's a coil that starts to carry the electricity, the electromagnetic induction. It generates the electricity, and then that will go through a load of circuit components, diodes, capacitors, etc., and it will charge the battery. And that is the basic principle of wireless charging. If you can get your phone onto the right sort of device here, then you can wirelessly charge your phone. The electric toothbrush is easy because you can simply put, like a lock and a key, you put the plug on top of the socket. Wireless phone, you put your phone on a whole mat or strip of something, and it doesn't matter which way round it is, it will still get charged. That's really, really difficult to do. Okay, but there is a wireless connection using a changing electromagnetic field that goes into the phone. That then produces a current inside the phone that will charge up the battery. but the technology up until a few years ago, it hasn't been that efficient. Yeah.
Does that mean that there's electricity flowing through the charger like all the time?
Yeah. Yeah.
Wow.
There is a magnetic, this is switched on, so there's a magnetic field here all the time. It's just nothing's happening with it. This is a waste of electricity.
Where'd you put the magnet? Or the
Yeah, if I put the magnet on there, I can make it do something useful. But you can see how inefficient it is. If there it's perfectly lined up, there I move it ever so slightly away, and the light goes off. So this is really, really inefficient.
What happens if you change it to DC now? Does it matter? No.
Why?
It won't work.
Why?
The electricity that is generated in this top part, the output coil, is caused by a changing magnetic field from here. It will only work with AC, okay? Because there's something called the conservation of energy, electromagnetic energy in physics. So when I've got a changing magnetic field here, I can induce forces on the electrons in this coil so that they will then start to move, and then they can form an electric current here. Okay. Now, if I have a very, very big voltage going in, depending on the sizes of these coils, if I've got more coils down here than I have up here, I can get a lower voltage coming out. And that's really useful when you've got cables that are taking 330,000 volts across the country. So you go skiing at Alra Maya and you're underneath those power lines. Yeah, those power lines have got hundreds of, probably about 10,000 volts actually on them. Plug anything into that and you fry it. So it has to go through a transformer to step it down to make it less. Yeah, this is a step down transformer from 230 to 5. Because we want 5 to plug in any micro USB devices. Any more than that, they don't work. And luckily, all micro USB devices have been agreed that 5 volts and usually 1 or 2 amps is what they work at. But sometimes we want to make the voltage bigger, like we want to send the power down the lines. So it comes out of the power station at maybe, I don't know, 500 volts. It's stepped up to 330,000 or so to be taken across the country. So we use it that way around. Usually, we don't play around with that. We don't use that. It's just done on an industrial scale, not on a household scale, because you don't want to have hundreds of thousands of volts. Yeah.
Do iPhones also use 5 volts?
Yeah, I think they do. But they have a different adapter because Apple just want to, I guess. Back to the old days where all sorts of mobile phones had different adapters, which was really, really, really annoying. I mean, the whole USB thing used to be, I can remember when USBs came out and being very, very grateful for USBs, because otherwise you had all sorts of different adapters and computers. And you could only have one input at a time. Okay, so how do we change something as ugly as this into something as small and beautiful and efficient as these? Because probably at home, anything that you've got that's got a charger, you may be running 20 of these at home or so. Okay, I have an old one here. That used to be the adapter, the plug. That was an old Motorola. This is the circuit inside. Okay, so the input goes in here. So I've got 200 volts across here. And it goes through this little device, which is our transformer. So, well, it doesn't look anything like that. Well, here's the outside casing. And the inside has got the input coil that's got 230, sorry, it's got the input coil, and and the output coil on top of each other. So our output is here, and then our input is wound around it, but there's a layer of plastic between it, so the coils don't actually touch physically. If they did, it would all get ruined. So it's like having this 400 wrapped around there. And that means that none of the magnetic field is wasted. There's a tiny iron core like this inside it. The magnetic field changes 50 times a second around here, then the current goes out, and these big cylindrical devices, anybody know what they are from any technical work? I don't know if you do them, they're called capacitors. Okay, and they store up the charge, and then you've got these diodes, not LEDs, not light emitting diodes, but you've got diodes that then change it into DC. So this changes the size of the voltage, it also changes the type into DC. Why is DC important? Because you want the voltage, the current going in one direction, because one direction is really important to charge up your battery. Your battery has to have a plus and a minus, so you need the electricity going from positive to negative all the time. If it changed positive to negative 50 times a second, you wouldn't get any charging at all. Does that make sense?
Yeah.
You all look mind blown. Okay, so any questions? No? Sure? You've gone quiet. You normally thought that William's not here. Maybe that's why you're not asking so many questions. Okay, so this was that's about 15 years old now. But the size hasn't gone down that much. Little bit. The components are getting better. Yeah.
Why haven't they like made it smaller?
It's a really, really good question. Probably expense. Possibly, with the size of the current and the voltage going through here, you're at the physical limits for the efficiency of the device. Yeah, you want to buy this so energy isn't wasted, so it doesn't get hot, and you want to pay. You know, how much would you pay for a charger? They come free with the device, I know, but 10 euros. Yeah. So economically, 10 euros is sensible. If you want to make this half price, half the size, it's going to be, I don't know, 40, 50 euros, because you're going to have to maybe have a different material inside here. These capacitors, they actually have a physical size limit for the job that they have to do. Sometimes you can buy capacitors that are absolutely huge, or you need many, many more of them. So it probably couldn't do its job properly. Also, if you make it too small, you've got a plug that nobody could actually handle. But electric circuitry has got almost to the limit of the sizes that it could physically be, given the dimensions of the wire and the components and things like that. I remember when the first, very ancient history, Sony Walkman cassettes came out. Yeah, so a cassette, have you ever seen, you've seen audio cassettes, maybe that big. The Sony Walkman, maybe that big. And the adverts were saying we couldn't make it any smaller because the cassette was too big. So it was being limited by the technology that at that time was carrying the music. And then portable CD players came out, which were pretty useless because they kept skipping and jumping all the time. So now change the medium in which the music is stored so that you can have your whole family's historic album connection on something the size of your thumbnail. And then actually what are you limited by? You're limited by probably the battery size and even the size of the adapter plug. So what have Apple done to the phone jack in their newest phones? They've got rid of it. Well, they're getting rid of it, aren't they? So you have to have Bluetooth earphones because the plug might the what's it, 3mm jack, whatever that size, that is spoiling the paper thin mobile phone. Where's it going to stop? Well, it's going to stop at the size of the whatever is carrying the memory.
What about the power chargers? My phone has gas charge. It's charged faster than normal phones. And is it that it comes out more on the side?
No, it comes out with a higher current. So
Like
what is
1.8?
yeah,
More than
1.8
2.
rather than maybe 1. So you can buy these power bricks now that have got a 1 amp output and a 2 amp output, and the 2 amp will charge it in half the time. But yeah, and that is down to the battery quality that's inside the power brick. If you've just got a fairly cheap rechargeable battery in there, then it's not going to charge it that quickly.
But the Nordic is that one, if you use 1 amps, it's just used for the full, but if you use 2 amps, it's just usually for
Tablet and things like that.
But if you use the 2 amps for the full, it creates the battery.
Yeah, the amount of current that you actually draw out of the device depends on the device that is attached to it. So if you've got a phone, it might be draining the battery far too quickly on the power brick. This is a very, very, very simplistic model here. That what you actually, you know, I left that on. It was getting quite hot. You've got the energy coming in. You've got a link here, and it's completely independent. It isn't completely independent, unfortunately. It's a little bit more complicated than that. So it depends on what the electrical is called, the load. So what I put on here will influence what the current is that is coming out of here. Maybe not the voltage, but the current, how quickly it can go through. And there used to be a time when rechargeable batteries, where you could get dull batteries because of the chemical reactions inside them, that they had this memory that you always had fully, and then you could use them. Whereas now you can charge them up to. You're recommended, aren't you, the first time you charge something, to charge it up fully. Why?
Yeah.
In a rechargeable battery, you're relying on chemical reactions going on inside the battery, and they're massively complicated, and they depend on all sorts of rare chemicals on the periodic table that each have ever so slightly different properties. Some of these, they have the batteries have what is called a memory, that if you don't shove them into the fully charged state for the first time that they're used, then they will never actually get there. It's bizarre. It's almost like they've got a character that they will refuse to go back there. And it used to be that you could, if you recharge the battery up to 3/4 full, you could never get it to fully charge. But now you have to charge them up once. And then if you charge it to 3/4 full, that's okay. It will drain the next time. It will go back to fully charged. But battery technology is really, really vulnerable, as Samsung know. So you've got to be pretty careful with anything that has got a rechargeable battery on. And you are advised not to leave old MacBooks, Mac laptops, Mac stuff. Well, iPhones are a bit better, but the MacBook batteries are notorious for, over time, decaying. Anything that you've got lurking around in storage at home that's got a rechargeable battery in it, at some point, 5 years, 10 years, 50 years, that battery is going to have a chemical reaction where it might leak out, it might explode. Yeah. There are really nasty, horrible chemicals inside those batteries.
When I'm gonna like
controller and then like the batteries, like the actual batteries, there's like exploded.
Yeah, and you get all this kind of white goo coming out. Yeah, only they're the simple ones. Batteries are toxic waste, which is why it's brilliant that you can take them back to any sort of shop. But if you've got, I had my mouse pad on my old MacBook wouldn't work. I hadn't used it for ages, and I wanted to get something off it, wouldn't work. It was like there was something pushing up from the side. Actually, a few days later, I noticed that this part was swollen inside.
That happened to my old iPhone.
It happened to your iPhone. Okay. I took out the battery, and it was swollen. It was beginning to blow up like a balloon. So I thought, is this going to catch fire? This is quite interesting. I'm a chemistry teacher. I wonder how this is going to go. So I kind of left it outside for a while, and it was getting bigger and bigger. And I thought, this is actually getting to be quite dangerous. So I did the stupid thing, and I just stuck a needle in it. And there are really nasty, toxic, horrible chemicals inside it. Don't do it. Yeah, take it to Rusco if that happens. Don't keep old
What could
rechargeable batteries.
What if you read those chemicals?
I didn't feel well afterwards. It was really acrid, horrible petrochemical burning plastic. Yuck. I had stupidly thought it's okay, it's just hydrogen, usually. Yeah, and that was what was worrying me. It's hydrogen, it's a flammable gas. And there's all sorts of, you get lithium and stuff like that inside them. But no, there's all sorts of things like fluorine and horrible organic chemicals inside there as well. It stank. It was really, really nasty and horrible. So do get rid of them. Don't leave them lying around. Now, that was an old battery. That was maybe 8-10 years old. Samsung, with its, Galaxy Note 7? Yeah, something was really wrong with the battery design there, and many of them exploded. So there was some unstable chemical in that batch, and it gave out hydrogen, there was some heat, and then the whole thing exploded. Now, the sad fact is, anything that uses a rechargeable battery, there is a chance, although a tiny chance, there is a chance that it is going to explode. You just don't want it while you're taking a call or something like that. So you do have to be very, very careful with them. These are massively nasty, toxic waste material. The developments are trying to make them safer. Really, really important. And it could just be the presence of a few atoms of these rare earth minerals that get mined in China that makes all the difference. And Samsung must have lost billions in its value, company value, and share prices because of that.
Isn't there like lots of videos about like people's like electronic secrets exploding?
Yeah. Yeah.
Because they like order it from like somewhere in China.
Yeah, I mean, to recall, your flagship product, that must be absolutely awful. Hey, you went to Nokia yesterday. What did you learn? Did you see any interesting physics? Or was it all about 5G? Hey, come on, that's interesting physics. Tell me about 5G.
They're like making like an accessible network that like can like has like an upload speed of like 16 gigabytes per second.
So you could download that from a video like 2 seconds.
Oh, life has changed so much. I can remember waiting 5 minutes for the first 3-minute MP3 that I downloaded. Now, why do we want such upload speeds?
Because we can like make we watched like the video of self-driving cars, and because like if we like it has like much more hertz, so it has a much more bigger refresh speed.
Yeah.
So like the camera of the car can refresh faster, and like there's no errors.
Yeah.
Like,
Yeah. More information, more possibilities for streaming.
Yeah, they also make like a cloud.
How do you handle the information that's gonna be in the internet? It's gonna be huge, and then someone decides to
It is.
network through.
There's also the matter of who owns it as well.
Then this could be done like.
Yeah.
They didn't tell us like they can't tell us how expensive it is.
No, and the price will drop.
And then we went to this lab which had like those, all kinds of electronics, and the heat it produced was
They had like a main, like a server.
server. The heat was so big that it was like 100 saunas. And so they had to lift the floor, and then the cooling was so high.
I know
Is
Google,
it the same like in those old kind of servers?
Yeah. yeah, working in huge great server rooms. That's why it's places like Google, because the cloud, it isn't a cloud up there. It doesn't. The cloud exists somewhere. Physically, your data is on a hard drive somewhere, and that has to be kept cooled down because you've got to have very fast access. Because if you want to show the video you just took of someone making a fool of themselves, you want to get it instantly, and it might actually be stored in northern Norway where it's cold. That's really good if it's cold.
Plan that they will put some servers underwater. It's so hot.
Yeah.
So they could do it underwater. It's always like the same.
Yeah.
Nearly the same.
Yeah. Or you can build it, you can have the server in a particular area, you can take the heat away and you can use it to heat up districts. Yeah. Okay, any, so Friday. Power stations on Friday. And bring back your Elmia books.